Now I'm going to talk a little bit about two popular dimension reduction techniques called principal component analysis and the singular value decomposition. These are two related dimension reduction techniques which can be used to take a large set of variables and compress them down into a smaller set of variables that are easier to interpret. So I'm going to start off with a random set of data that I've assigned to this matrix. So you could imagine this is a data matrix where there's absolutely no relationship between the variables or the observations. Here, in each row is an observation, and in each column is a variable. And the color represents what the value of that variable is for that observation. So for example, this upper left-hand corner represents the value for the first variable and the first observation. So you can see in this matrix visually that there doesn't appear to be any pattern relating the variables or the observations. And in fact, you can even cluster the data set, and you can see that there doesn't appear to be any strong patterns even once the data are clustered. There don't appear to be any sort of clumps of color with the exception of this small little clump of yellow here at the bottom of the data set. What we can do then is actually add in a particular pattern that affects some of the rows of this data set. So the way that we do that is we run through all 40 rows of the data set, and for each row we flip a coin. We do that by generating one binomial random variable with an equal probability of being equal to 0 or 1. If the coin flip is equal to 1, we add to that row of the data matrix a particular pattern, such that the value of the first 5 variables we add 0 to, and the last 5 variables we add 3 to. So this means that for some of the rows of this matrix, there's a particular pattern that looks like 0 for the first 5 elements and 3 for the last 5 elements. Looking at this visually, this is what the matrix looks like once we've added that pattern in. So you can see that for some of these rows, it looks like the values are somewhat smaller for the first 5 columns and somewhat larger for the last 5 columns. You can see it isn't true for every row because we flipped a coin, and each time we flipped the coin, we decided whether to add that pattern or not. Once you perform a clustering, you can actually see that the pattern appears now to separate out the two sets of observations, the first 5 set of variables and the last 5 set of variables. You can see now that these are the rows, everything above this line right here appear to be the rows where we've added that pattern. So we added a pattern of 0 plus 3 to the first 5 and the last 5. So what we want to do is maybe be able to determine what that pattern is. We've only added a very small pattern. We haven't added a very complicated pattern at all. We might want to be able to determine what that pattern is without reporting the entire data set in the form of this heat map. So the first thing that we could do is we could actually just take the means of the rows and the means of the columns. So again, this is the data matrix here. And what I've done is I've taken the mean of each row and I've plotted it here. So what you can see is the first several rows, you can see that they have a higher mean, and that's because to these rows I've added the pattern which was only positive values to some of the columns. You can also plot for each column its mean, and what you see is that the column means for the first set of variables might be slightly smaller than the column means for the second set of variables because we've added a particular value that's positive only to the last 5 variables. So you can see the pattern in both the columns and the rows by taking the means. But what happens if there's more than one pattern, and is this the best way to describe the patterns or to compress the patterns in this data matrix? It turns out there are two related problems that show the best way to compress a data matrix depending on what your definition of compression is. So you can imagine you have a multivariate set of variables. So here, each variable x1 to xn represents all the observations in one column of that matrix. So x1 is actually equal to a larger set of values, x11 down to x1m, and these values represent all the values in the first column of the matrix. So there are two related goals. One, you could try to find a new set of variables, not the x's, but some other set of variables that are uncorrelated and explain as much variance as possible. You could also put all of the variables together in one matrix like we did on those previous slides, and then try to find the best matrix created with fewer variables, or a matrix of what's called lower rank that explains the original data. The first goal is a statistical goal, and the second goal is a data compression goal, but it turns out that the solutions to these two problems are related. So the first approach, the singular value decomposition, compresses the data by performing a matrix decomposition. Don't be too intimidated by what a matrix decomposition is in terms of math. You primarily need to be concerned with knowing that this decomposition has three parts: the U, or the left singular vectors, the D, the singular values, and the V, which are the right singular vectors. The principal components of a matrix are actually equal to the right singular vectors if you first scale and the variables by the appropriate quantities before performing the singular value decomposition. In other words, the SVD and PCA are actually solutions that give you the same solutions if you perform the right pre-processing first. So first I'm going to talk a little bit about the singular value decomposition, and I'm going to talk about two of those components, the U component and the V component. U is called the left singular vectors, and V is called the right singular vectors. In R, to calculate the singular value decomposition of a matrix, you use the command SVD. So here I've applied SVD to our scaled matrix. I then make a plot first of the entire data matrix using the image command. Then I plot the first left singular vector, which is the first column of the U component of the list that results when you apply SVD to a matrix in R. Then I also plot the first column of the V matrix, or the right singular vectors, that also is a part of the list that gets created when you apply SVD to a matrix in R. The left singular vectors appear to show that same pattern that the row means showed earlier. The first set of rows is different from the second set of rows, and that corresponds to the rows that got the pattern added to them versus the rows that didn't have the pattern added to them. Here the scale isn't the same, so it's not positive and negative don't necessarily mean the same thing that they did previously. You can just see the visual pattern of the difference between the columns. Right. Then you can also look at the difference between the patterns that you see across the rows. So this is the right singular vectors plotted by column. And so what you can see is the last five columns of this matrix all have a particular value, whereas the first five columns all seem to have some more variation. This makes sense because we've added a specific value, 3, to the last several of the rows of the last 5 columns, but we did not add any values to the first columns, and so they still represent random noise. We can also look at the D component that comes out of the singular value decomposition. So if we apply the SVD to the data matrix, and then we make a plot of the D values by column, we can see that they're a decreasing set of values. So these decreasing set of values start with the first right singular vector or left singular vector corresponds to this first D value. The second right singular vector or left singular vector corresponds to this value, and so forth. If you actually plot, instead of D, you plot D squared divided by the sum of the D squareds, this actually corresponds to the percent variance explained by a particular column or row of the singular vectors. So what you can see is that the first right and left singular vector together explain about 40% of the variance in that matrix. The second right and left singular vectors explain much less variance. They only explain about 15% of the variance in the matrix, and so forth. This is important a plot because you can actually go and see how many patterns are actually appear to explain most of the variation in the data set. One thing that people do often is they add up the cumulative amount of variance explained moving from left to right, and they identify all the patterns that explain some large percentage of the variance, say 80 or 90%, and then they can compress their data down by only considering the components of the singular value decomposition that represent those patterns. So just to show you the relationship between singular value decomposition and principal components, here I've actually calculated the singular value decomposition on the scaled matrix, and I've also calculated the principal components on the same matrix, also scaled. And if I plot the first principal component, which you can get from the rotation matrix in the PCA1 object, versus the first right singular vector from the SVD object, you see that they're exactly the same. They actually lie directly on the 45-degree line, and there's no difference between them. So performing a singular value decomposition is equivalent to performing a principal component analysis in this case. Now a little bit more about how the singular value decomposition variance is calculated. So imagine that I create a constant matrix. In other words, I create a matrix where every row is identically the same, where each row has 5 values of 0 followed by 5 values of 1. If I then calculate the singular value decomposition of this matrix, and I plot the d values, you can see that there's only one d value that stands out much above the others. It turns out that that actually explains 100% of the variance in this matrix. The reason why is, if I take only the first right singular vector and first left singular vector and multiply them together, I can reproduce this matrix exactly. So all of the variation in this matrix is explained by exactly one pattern. Alternatively, if the data was exactly random, each singular value or each singular vector would explain approximately 1 over the number of columns variance in the data set. So what if we add a second pattern to the data set? What happens to the singular values and singular vectors? So again, I've performed an analysis where I loop through each of the rows of the data set, and now I perform 2 coin flips. If coin flip 1 is true, then I add a pattern that has 5 zeros followed by 5 fives to the data set. If the second coin flip is true, I add a pattern that is equal to 0, 5, 0, 5, 0, 5 repeated over and over again. So I can then cluster the data set and make a plot of that clustering. And you can see that there are now 2 patterns in this data set. You can see there are some rows where there's a pattern such that the values are low on the left-hand side and high on the right-hand side. You can see that there's also a second pattern that's this striped pattern. So it goes low, high, low, high, low, high. And these 2 patterns overlap each other. So you can see that the 2 patterns are given here on the right in these 2 plots. So pattern 1 is low for the first 5 columns and then high for the next 5 columns. Pattern 2 goes low, high, low, high, low, high. So what happens if we perform the singular value decomposition on this matrix? We can actually plot the right singular vectors of this matrix, and they look like this. So here what's going on is that the 2 singular vectors actually represent a combination of the patterns that went into creating this matrix. So you can see, for example, that these values go low, high, low, high, low, high, low, high, low, high, but they also have the first 5 values are lower than the second 5 values. So you can see that that's a combination of the 2 patterns that were used to create this data set. Similarly, the second right singular vector also is a combination of these 2 patterns, but where the pattern is flipped. Taken together, these 2 patterns explain most of the variation that is going on in this data matrix. You can see that in the percent of variance explained. So if we take the singular value decomposition of our new matrix, so that has 2 patterns in it, and plot the singular values, we can see that they go from large to small. And again, the first 2 values explain most of the variance, as you can see in this plot. The first value explains 50% of the variance, and the second value explains almost 20% of the variance. And then the next several values also explain a small percentage of the variance, but it's much lower. So what this would suggest is that there are 2 patterns in the data set, but they aren't necessarily the 2 patterns that we observed in the singular values or singular vectors. Remember, each of the singular vectors might represent multiple patterns mashed together. You can actually perform the singular value decomposition much faster when the data set is built so that either the number of rows is much smaller than the number of columns, or the number of columns is much smaller than the number of rows. Here I've created a larger matrix, big matrix, that has 10,000 rows and 40 columns, so the number of rows is much larger than the number of columns. If I perform the singular value decomposition on this big matrix object, I see that it takes about 0.16 seconds to perform that operation. If I use the fast.svd function, it actually performs the calculation substantially faster, so 0.127 seconds. This doesn't seem like much of a difference, but if the matrices get much larger than this, it can be much, much larger in terms of the computation time. Here I've set the tolerance to be equal to 0 because the fast.svd only calculates singular values and singular vectors for values above the tolerance. If you set the tolerance to be equal to 0, it will calculate all the singular values and singular vectors. An important note is that the singular value decomposition cannot be performed on values on data sets with missing values. So here I've generated a data matrix that has some of the values equal to missing values. So I've set them equal to NA. I can then try to perform the singular value decomposition on this matrix, but it returns an error because there are missing values. So one option is, if you have missing values in your matrix, is that you can impute those missing values. There are a large number of ways to impute data, and there's a large literature on missing data. But for the purposes of exploratory analysis, one quick way to impute the missing data is to use the impute package and to use the impute.knn function. So here I've created a data matrix which has some missing values, and then I can use the impute.knn function applied to the data set with missing values and return the completed data set which has imputed those data values with a k-nearest neighbors imputation approach. I'm not going to go into the details of the k-nearest neighbors imputation approach here, but suffice it to say, it uses vectors of variables that are nearby that are complete observations to impute the values that are missing in the data set. You can then perform the singular value decomposition on both the original data set and the data set that had missing values imputed with k-nearest neighbors, and then plot the first right singular vector of both of those analyses. You can see that they're very, very similar to each other. In other words, by imputing and then performing the singular value decomposition, you get very similar results to what you would have gotten if you had not imputed, if you had the complete original data set. Of course, this works in this very contrived example, very simple example, but in general it might not always work, particularly if you have a large number of missing data, or if there's a pattern of missing data that's related to some of the variables that exist in your data set. So now I'm going to show you one quick example of why this sort of singular value decomposition can be very useful and cool. So what I'm going to do is I'm going to actually use an example where I've downloaded a particular FACE data set from the course website. Sorry, this got cut off a little bit, but I've just saved this as a file face.rda on my in my data folder here. So then what I do is I load the FACE data using the load command. And if I look at an image of that data, I can actually see that this data matrix actually looks like a person's face. And so what this is actually a picture that has been, where all of the pixels intensities have been saved into this data matrix. So if I perform a singular value decomposition on this FACE data set, and then I look at the percentage of variance explained, I can see that the first, second, third, fourth, and fifth variables all explain a large percentage of the variance. So what I can do now is I can actually reconstruct versions of this FACE where I only use the first singular vector, where I use the first 5 singular vectors to reconstruct the FACE, or I use the first 10 singular vectors to reconstruct the FACE. If I only use the first singular vector, I've actually reduced the amount of data I have to store dramatically, since I only have to store one right singular vector and one left singular vector rather than the whole data set. Similarly, if I only have to store 5 right singular vectors and 5 left singular vectors, I've still reduced the amount of data that I have to store. And so I've actually compressed the information that I have on this FACE. So to create the approximations, I first calculate the singular value decomposition, and then I perform a specific set of matrix multiplications that are represented by the matrix multiplication that I explained in math earlier in the talk. So basically I take U times V times D. In the case of where you have multiple vectors, I actually matrix multiply U times a diagonal matrix with D on the diagonal and times the V matrix transpose. So this exactly maps to the UDV transpose definition of the singular value decomposition that I gave in mathematics at the beginning of the talk. So I have an approximation with one singular vector, with 5 singular vectors, and with 10 singular vectors, and I can show you what those look like in terms of images. So on the left here, you actually see the original image itself. The next picture over you see is the image that you get if you actually only include the top 10 singular vectors. So what we've done here is we've eliminated a lot of the data and stored only a much smaller subset of the data, and you can see that you get very close to the original image itself. Remember that 5 singular vectors represented most of the variance in the image, and so if you use the first 5 singular vectors, you can actually reconstruct a very close approximation to the original FACE data set. If you only use one singular vector, you actually don't see the face very well at all, because all it captures is the fact that this part of the image actually has higher values than the other part. So what you can see here is, as you increase the number of singular vectors that you use, you get closer and closer approximations to the original face. So I've talked a lot about the singular value decomposition and principal component analysis. The right singular vectors of a data matrix or the left singular vectors of a data matrix can be used to represent common patterns in the data sets. But remember that the principal components or singular vectors may represent a mix of the real patterns that were used to generate the data set. So you have to pay a little bit of attention and be careful in interpreting singular vectors as corresponding to a particular observed variable. It can be computationally intensive, but I talked a little bit about the fast.svd function for making it a little bit faster when either the rows or columns are much larger. Here I've pointed to a resource, Advanced Data Analysis from an Elementary Point of View, that goes into much more mathematical detail and much more detail about the singular value decomposition and principal component analysis, as well as a book, Elements of Machine Learning, that also covers a lot of those details. There are a large number of alternatives for dimension reduction and also for understanding patterns in a dataset, including factor analysis, independent component analysis, or latent semantic analysis, and I've given you links here to each of these different kinds of analyses in this file.